Hello friends, welcome to Piping Engineers. In today's video, we will learn about pump affinity laws and their calculations. We will learn what are pump affinity laws, what are the various terms involved in pump affinity laws, how those terms are calculated, and what is the impact of each term on the pumping system. So for more updates and videos, please like, follow and subscribe our channel. So let's move on to our today's video and learn about the pumps. So friends, what is a pump? Pump you would have seen in your day-to-day life. You would have seen pumps at your houses, in schools, colleges or in industries. So pump is basically a mechanical device that is used to move fluids, solid waste, chemicals, slurries by mechanical action from one place to another. So while selecting a pump, there are two important components that are kept in mind. So one of the component is flow and other is head. So what a flow is, flow determines the amount of fluid to be pumped from one place to another. So flow tells the amount of fluid that we want get transported from one place to another. So that is the flow of the pump. And what head is, head tells the extent or distance to which my fluid is to be exported. So while calculating the flow and head, there are some important parameters that we keep in mind, that what will be the viscosity of the my fluid, what how my piping would be, what number of bends. So that we have covered in separate video of pump head loss. So moving on to another, there are two types of pumps based on their operating principles. One is dynamic pumps and other is displacement pumps. Dynamic pumps, around 80 to 90% of pumps used in industries, they are dynamic pumps. Dynamic pumps can further be classified as centrifugal pumps, vertical centrifugal pumps and submersible pumps, and many more to come. So talking about these centrifugal pumps, around 80 to 90% of industrial operations are carried out by the centrifugal pumps. Because of their low capex and opex and ease of maintenance, centrifugal pumps are used widely in the industrial processes. And displacement pumps can further be classified as gear pumps, piston pumps, lobe pumps, etc. So gear pumps are used for some specific purpose where centrifugal pumps can't serve the purpose. So while having some special type of slurries or some special chemicals, we go for displacement pumps. For example, if we want to transport coal tar in my steel plant from one place to another, I'll be going for a positive displacement pump. One disadvantage with positive displacement pump is that they are having a very high maintenance cost, and their maintenance precision is also very high, and also the worker that will be doing maintenance should be very skillful. Hence displacement pumps, they are not used generally in the industrial processes until and unless some specific demand of operation is there. So I have kept some pictures here. So one, this type of this pump which is shown here is your centrifugal pump. There are two types of centrifugal pump. One is this one is this front suction and top discharge, and another is having this here side suction, and parallel to this suction there is a side discharge in the pump. This is a submersible pump. In submersible pump, both motor and impeller, they are enclosed in this cylindrical housing, and this housing is completely submerged in the water. Hence its name is derived from that submergence only. It is known as submersible pump. This pipe type of pump is known as lobe pump, and this lobe moves the fluid from one point to another in the system. So moving on to our affinity laws and see what are affinity laws. So what are affinity laws? Affinity laws are set of formulas that predict the impact of change in impeller diameter and rotational speed on the pump head, flow produced by pump, and power determined by the pump. So there are two things. One is impeller diameter and rotational speed. When these terms are changed, when these two components are changed in a pump, so there will be some impact on my pump head, there will be impact on my flow produced by pump and power demanded by the pump. Hence the affinity laws are framed, once keeping the diameter constant and once keeping rotational speed constant. So while diameter is kept constant, my rotational speed will change, and when my rotational speed is kept constant, my diameter will change. So moving on to next, our first segment, we have made the first affinity law while keeping the constant impeller diameter. So if my constant diameter is there, there will be some change in my rotational speed. So first part is, let's see the impact of rotational speed on the flow. Flow pump is directly proportional to the change in speed of pump. So whenever my rotational speed is changed, there will be a directly proportional relation in flow. So how much the rotational speed is changed, same flow amount of flow will also get changed. These affinity laws are applicable to certain same family of pumps. So whenever a supplier supplies a pump, he supplies a pumps under the family of pumps in which the basic properties of the pumps are same. So suppose I am having a pump which is having my Q1 flow, it is providing at N1 RPM, and because of same family of the pumps I want to change the flow. So when I change the flow there will be same change in the RPM also. Hence this Q1 is my older flow, N1 is my older RPM, Q2 is my new flow, and there will be similarly there will be change in my N2. So these are basically used under the same family of pumps. So hence we can't use it to, like if I'm having some pump, some flow is there, or I want to change that flow abruptly, we can't use those laws under different conditions while without knowing the basic characteristic curves of the pump. Next is, let's see the impact on head. Head of pump is proportional to the square of speed. So the head is directly proportional to the n square, or one hand h1 is proportional to n1 square, or h2 is proportional to n2 square. So power impact, power is proportional to the cube of speed. So there will be an 8 times change in my power whenever I will be changing the rotational speed. At the later end of video with the example I will be making it clear. So moving to this curve, let me tell you this, let me show you one thing. Suppose I have selected a pump at, in which the RPM is 1480 RPM and my flow is 1600 meter cube per hour. So at 1600 meter cube per hour, efficiency of my pump is 83% and my pump power is 100 kilowatt. But I want to change my flow to suppose 400 meter cube per hour. So at 400 meter cube per hour, what will be the new RPM? So my new RPM will be, if I move there, my new RPM will be around 1350. So new RPM will be 1350 and my flow is reduced. So similarly you can see, as it is mentioned here, it is a direct relation. So as my flow is reduced, my RPM is also reduced, and same way my efficiency also get reduced. In my 600 pump, efficiency was 83%, but now it is coming around 72 or 73%. So hence this relation can be derived from this pump curve also. So moving on to next, let's see the impact of pump affinity law keeping the rotational speed constant. So when the rotational speed is constant, so we have similar relation as we had on our flow, head and power in while keeping the impeller diameter constant. So flow pump is directly proportional to the change in impeller diameter. Hence my whenever I change the impeller diameter, a same change will can be seen in my flow also. So Q1 is equal to D1 by Q2 equal to D2. And same when moving to head of pump is proportional to the square of impeller diameter, as it was same in the RPM also. H is directly proportional to D square, or H1 by H2 is equal to D1 square by D2 square. Similarly power is proportional to the cube of impeller diameter, as it was in the case of rotational speed. Power is inversely proportional to the cube root of the impeller change diameter. So P1 by P2 is equal to D1 cube by D2 cube. Hence the formulas are same, but in place of RPM we have placed the diameters. Where in previous slide we have seen it was N1 by N2, and here it is D1 by D2. So let's see this graph here and try to learn the thing. So suppose I have a pump in which the RPM, in which the impeller diameter which I have selected is 4000 mm, and at 4000 mm suppose I have selected the 600 meter cube flow and my pump efficiency is 83% and my power consumption is around 100 kilowatt. Now what happens is I just want to change my flow. So my flow, I have changed my flow to 600, I have changed my flow to 600 meter cube per hour. So at 600 meter cube per hour my new impeller diameter will be around 373 mm, and my head is will be around less than 50 meter water column, and my new power consumption will be less than 100 or around 70 kilowatt, and my efficiency of pump will also goes down. Hence while changing the impeller diameter, suppose I am decreasing my flow, my impeller diameter will, if I am decreasing my impeller diameter, my flow will also get decreased, my power consumption will also get decreased, and vice versa. So if I am increasing my flow, my impeller diameter will also get increased and my power consumption will be increased by 8 times. So what is the basic application of this affinity law? So affinity law is used in impeller trimming of the same family of pumps, is done based on the calculation of pump affinity law. So if I'm having a certain flow, let's say I'm having a flow at 1000 meter cube per hour, and my Q2, I want to have this Q2, and at 100 meter cube per hour my diameter is 100 mm or zero point 0.1, and suppose I want to change my I want to have a new flow around 200. So when I'll be changing this flow to Q2 to 200, so there will be certain increase in my D2 also. So this relation helps us changing the impeller of the pump without changing the complete pump. But the condition is that the impeller can be changed only under the same family of pumps. I can't change the impeller abruptly without knowing the family curves for the pump. So impeller trimming is used in while maintaining the pumps if you want to increase or decrease the to decrease or increase the flow of a pump without changing the complete pump. And there will be the similar changes on the head of the pump and power of the pump, as these laws are directly proportional to the heads and power consumption. So let's move to the next slide and see the example. So this is composite pump affinity law. As I told you that Q1 is directly proportional to N1 and it is directly proportional to D1 also. So combining the equation, Q1 is equal to N1 into D1 by Q2 is equal to N2 into D2. Similarly, H1 is equal to N1 D1 square, H2 is equal to N2 D2 square, P1 N1 D1 cube and P2 N2 D2 cube. I have just combined my constant speed and constant impeller diameter equations and formulated this composite equation. So this composite equation is used whenever I have a change in impeller diameter also, and RPM of the pump is also in changing at the same time, and if I am having all the four values and I want to want to calculate the fifth value. So this equations, they are very helpful while making the changes of a running while making the changes in the running pump, and without changing the pump I want to use the same pump and getting the best out of it. So pump affinity laws are basically used there. So I have made an example. Let's see, consider a pump of flow 100 meter cube per hour. It is designed for 1500 rpm. The same pump is required to be operated at 3000 rpm. Find the changed flow of pump. Assume the diameter of pump is kept constant. So as per affinity law, when impeller diameter is kept constant, as I already told you, Q1 is directly proportional to N. Q1 by equal to N1 and Q2 equal to N2. So Q1 is 1000 meter cube, N1 is 1500 rpm, N2 I have got here 3000 rpm, and Q2 question mark. So you can see if I just put the values, so Q2 will be 2000 meter cube per hour. So you can see that rpm here has increased twice. So similarly my flow has also increased twice. So that is, it is directly proportional, because it is directly proportional, the q is directly proportional to speed. So hence, as the value of my speed has increased, similar value of my flow has also increased. So let's see for the power consumption what will happen. Let's take power consumption equal to 1000 kilowatts. So P2 at the changed RPM. So as already told, power is directly proportional to N cube. P1 by P2 is equal to N1 cube by N2 cube. So at 1500 RPM, my power consumption was 100 kilowatt. So what will be my power consumption at 2000 cube rpm, 3000 cube rpm? So it will be P2 is equal to 800 kilowatts. So that means whenever my there will be a change in rpm, the twice the change in rpm, it will increase my power 8 times. So 2 to the cube of there will be a power increase of 2 to the power 3 times. So 2 cube will be my power, hence the power consumption of pump will be 8 times. So hence, without changing the pump, without going into a practical situation, with these formulas we can calculate what will be the impact on my pump, and with the help of some pump family curves and pump equations. So friends, I hope you would have learned about the pump affinity laws, what are their advantages, how they are used in industries, and what is their benefit of using. So for more updates and videos, please like, follow and subscribe our channel. So friends, thank you for the day. Thanks a lot.